Welcome back to Calculus 2. Section 2.3, Cylindrical Shells. In this video, we'll go over two topics. We'll look at the method of cylindrical shells, revolving about an axis, and then we'll come back and we'll talk about what if we were to revolve about an arbitrary line. Let's start with the basic version, revolving about an axis. We want to start by considering a cylindrical shell. What do we mean by that? Here we're looking at a picture of a cylinder. The cylinder has a radius. The cylinder has a height. What do we mean by a cylindrical shell is that we're only going to consider the walls of the cylinder, but not the top nor the bottom, just the walls. That is a cylindrical shell. Very nice. Let's cut vertically this cylindrical shell and then lay it flat. Doing so will produce a rectangle. What are the measurements of the rectangle? Well, the height of the cylindrical shell is the height of this rectangle. How about the length? For the length, that is coming from the circumference of this circle. And we know the formula for the circumference is 2 pi r. So the length is 2 pi r. The height is h. And the area of the rectangle is 2 pi rh. Perfect. Orient the cylindrical shell such that the axis in the plane occurs with the axis of rotation for the cylindrical shell, and place the base at the x-axis. Doing so, we could then find that x will measure the radius, and then for the height of the cylindrical shell, let's suppose that this height occurs along some graph y equal f of x. That's the height. Let's watch this point revolve about this circle. So how can we produce this cylindrical shell if we're provided with the graph of a function? We can pick a point in the domain of the function, let that be a radius value, and then take f of x to be a height value. Then consider this point and everything below it down to the x-axis, and watch it revolve about a circle of distance of radius x away from the y-axis. Good. And that's how we can produce a cylindrical shell provided a function f of x. Nice. And then let's consider various other cylindrical shells taken at different points along the curve y equal f of x. So here's a cylindrical shell taken at a different point corresponding with an x value, which is giving a smaller radius but a larger height, and yet again a smaller radius and a larger height. Let's identify the radii as points in a partition. Good. And then let's consider the shell having a volume by letting x be two consecutive points in a partition. How far apart are these 2 points? Delta x. And then the inner cylindrical shell. Let it have the same height. And now let's go about thinking, well, in between these two cylindrical shells, how much volume is determined? All right. So we want to know the volume of the shell, which we're now taking to have volume. Right? And we're going to use the familiar big minus small. Well, what do we mean by that? We have an outer shell with a large radius xi. So V big will be pi r squared, pi xi squared, times the height. And the inner shell will have a radius xi minus 1, giving a volume small as pi r squared, pi x sub I minus 1 squared, times height, f of xi. Note that it's f of xi. Good. Now we do algebra. We can factor off a pi, and we can factor off an f of xi. That produces a binomial, which we can use the difference of squares formula to factor it. We can recognize the difference as delta x. And we can take this sum, xi plus xi minus 1, and rephrase it as twice the sum of xi and xi minus 1 over 2. And then this quantity is the average value of these 2 points. And then that average value would occur between the two values. Thus, it's appropriate to name that xi star. And we've swapped out the difference xi minus 1 as delta x. Very good. What have we computed? We've computed the volume contained between these two cylindrical shells. Good. So introduce notation V sub I. You have 2 points in a partition. You have a function, f of x. That information can be used to then find the volume of a cylindrical shell, determined by the points in the partition and the function f of x. And if we compute the volume of each of these approximations, V sub i's, add them up, and get an approximation to the volume produced by revolving this region under y equal f of x about the y-axis. Note that we're integrating on x, but we're taking this curve produced as a function of this interval on x and revolving that region about the y-axis. Okay. Come in and substitute our formula that we found for V sub I. This is forming up a nice Riemann sum. The 2 pi xi star f of xi, that's going to become the integrand. The delta x is going to become the differential dx. 2 pi is a constant. We can bring that to the front, apply a limit to this Riemann sum, and rephrase it as an integral. Perfect. Okay, let's formally write down what we've gone over. So this is the method of cylindrical shells. We want f to be continuous and non-negative. And then we take r to be the region, bounded above by the graph of f, bounded below by the x-axis, and off to the left and right by x equals a and x equals b, respectively. The volume of the solid formed by revolving capital R about the y-axis is then given by this volume integral. Note that the constant out in front is 2 pi. That corresponds with the revolution about the y-axis, producing a circle which has circumference 2 pi r, where r was being swapped out for x as the radius, and then f of x is giving the height of the shell. Good. So with that, the 2 pi r times h is the area of the rectangle corresponding with any given cylindrical shell formed at location x. Perfect. Let's do an example. In the previous video, we used this reciprocal function, y equal 1 over x. We formed up this region R over the interval 1 to 2. And in the previous video, we revolved about the x-axis, and that produced Gabriel's horn. Here, in contrast, the cylindrical shells method is to look at the graph of a function over an interval, here x, but then revolve about a line perpendicular to that interval. Okay. What is the volume integral in the method of cylindrical shells? There's a constant out in front, 2 pi. So think 2 pi radius and then height. We have a bounds of integration, a to b. In this case, we're going to use 1 and 2. X is just x, and then f of x we swap out with 1 over x. Make a note of that. F of x is 1 over x. Bounds are 1 and 2. Plug in. X times f of x becomes constant 1. Integrating 1 from 1 to 2 is 1. Times 2 pi produces 2 pi. You may recall last time Gabriel's horn over this interval had volume pi over 2. Very good. And then here's a picture of the solid that was produced. The y-axis would occur here in the center, and this center portion has been hollowed out where we only revolved this region under the curve y equal 1 over x. Nice. Your turn. To make sure that you're on solid footing, come up with the volume of a cylinder using the method of cylindrical shells. Then make adjustments to that computation in order to use the method of shells to produce the volume of an ellipse. As well as the volume of a cone. Fantastic. So that's the method of cylindrical shells. We'll now challenge ourselves by changing the axis of revolution from the y-axis to an arbitrary line. Okay. And to do so, we'll let our region R occur underneath y equal x over the interval 1 to 2. And we started out by revolving about the y-axis. We could note that the y-axis is given by the equation x equals 0. we want to consider a different vertical line. Let's say, for example, x equals -1. Now, if we pick a point in our interval of integration, x, then we need to figure out how far away is x from the axis of rotation. If we come back and think of the case that we've already covered, revolving about the y-axis, this distance would be exactly x. That would be the radius. But we want to consider the axis of rotation to be x equals -1. Thus, the radius would grow by 1. We can also view this as big minus small, so that x minus -1 produces a radius of x plus 1. Very good. So here is, in words, the task in front of us. Compute the volume of the solid generated by revolving the region R about the line x equals -1. Okay. Well, as the region R is defined over this interval of x's between 1 and 2, but we want to revolve about this vertical line, that's suggesting that we use the method of cylindrical shells. What's the volume integral for the method of cylindrical shells? 2 pi, definite integral, bounds of integration, integrand as functions of x, radius, product, height. We've already established what the radius is, so we can swap that out. Then we need to look at our particular arbitrary input x. And then how high would the height of the shell be? That's given by the function f. In this case, it has a simple form, x. So plug in the radius, plug in the height, and we're done. We've set up our integral. Having it set up, straightforward to evaluate. And we have computed volume by revolving about an arbitrary line. Nice. Now it's your turn. So again, just a slight modification in the height function. Otherwise, things are basically the same. And then let's alter our setup slightly. Let's take a region which is bounded by the graph of two different functions, x and x squared. Let's pick an arbitrary point in the interval of integration. And then we can look at a vertical line entering and exiting the region. It would enter along the parabola y equals x squared and exit along the linear y equal x. Therefore, what is the height of this line segment? It says height, so we'd want to take big Y minus small y, or x minus x squared. That'd be the height of the line segment. And in this problem, what are we doing? We're revolving about the y-axis. So how far is this line segment from the axis of rotation? It's exactly x away. In other words, x is the radius. Here's a picture of the cylindrical shell. Use the generic volume integral for the method of cylindrical shells. For the radius, we've established that's x, and for the height, we've established that's x minus x squared. Boom. Done. Our integral is set up. Straightforward to evaluate. And we're finished. Meaning it's your turn. Now, the region R is, in this assignment, bounded by x and x cubed. However, instead of revolving about the x-axis, in this problem, revolve about the line x equals 2. And if you apply the concept of big minus small, this problem should also go through without any problems. Fantastic. This brings us to the end of the video. Thank you so much for watching. Please like if you've found this video helpful. And see you on the next one.